Now, before we go, what we want to do today is we want to derive the continuity equation and relate it to the diffusion length and to the diffusion coefficient. Before we do that, what we are saying, we're saying that the excess carrier, if we are talking about N or P, we refer to them as carrier. We say the excess carrier is equal to the new concentration of electron minus the equilibrium value, meaning when N was equal to P, so that's N0, we refer to it, depending if we are talking about N-type material or P-type material. And if we have a neutrality condition, then we say that then delta N equal to delta P. So now we want to derive the continuity equation. We say we will consider carrier flux into and out of this particular volume that you see here. Okay, so that bar of semiconductor, when we are saying that, and is there a question? Okay, if we have a current flowing into the semiconductor through a thickness of dx and a cross-sectional area A, then we say that this current Jn of x, as it passes through the material in and out of the material, it becomes out of the material equal to Jn of x plus dx, passing through a volume of A dx. This implies that the excess carrier that was in the semiconductor then have a loss rate. We say that the loss rate is equal to del n over tau n dot dx. We know that this is the flow rate, but it's the flow rate of the loss rate. Okay, we know that we always refer to the rate as del n. When we saw in the previous slides before of this lecture, we saw how we obtain the rate of recombination or the spontaneous rate. We call it, it was the del over the tau. Okay, so in that then, we said, if I want to obtain the total flow rate inside this semiconductor, then we say the total flow rate, which is the change of N by T by the time multiplied by the volume, so is equal to the, as well, we're talking here about the flux, the flow rate. So here it is, we know that the flux is equal to what? Equal to the current over the charge multiplied by the area. So in this case, we have the change from here to there, you know, this in, that out. So what's inside the semiconductor is a Jn of x minus a Jn of x plus dx, all multiplied by the area A divided by the charge E. So that gives me the flux. And of course, the negative sign, because we're talking about electrons, and the total flow rate will be this, the charge, the flow rate due to the current minus the flow rate due to the loss rate. Okay. So we're saying then the total flow rate equal to the flow rate of current minus the loss rate. Okay, so if we write it down, then we want to know what's Jn of x plus dx equal to. It's equal to Jn of x plus the change of Jn of x over del x multiplied by dx, so that is the term, this one. We put it in this form, then we can obtain by dividing by del x, we will obtain dividing by the volume actually, so dn by dt equal to 1 over e jn of x by dx. When we added this term to the other term, to the one before, I will go back just to show you. So this is a jn of x minus a jn of x plus dx. So we factored this part, we partitioned this part, taking it from there, and then what we will be left with is then this term here, which is 1 over e, the minus sign got out from this equation, since there was minus, minus became plus. So del n of by del t equal to 1 over e del jn of x by dx minus delta n over tau n. And of course, if I write this term for electrons, I can deduce the one for holes. So from electron, the only term will be having for the Jp will end up with minus, since we didn't have minus at the equation. If you want, if I want to show you back, in here we have this minus sign for the n, so for the p we will not have this minus sign, and that's why we will end up with only one minus, which will show us the minus sign here. Okay, so now I have a term which relates the flow rate to the current and the loss rate for electrons and for holes. And then I can say this is referred to as the continuity equation. So the continuity equation is written as the change of electron per time equal to the current or to the flux due to the, or the flow rate of current due to current minus the loss rate, and the same thing for holes. So now if we want to derive for minority carrier, and we're only talking about diffusion only, so we will write the equation and we will say, okay, the electric field in this case is a small, so this equation, which referred to as the current due to electrons for a p-type material, because we are talking now, you're telling you might say it's n, why you call it p-type material. We said for minority carrier. What's the minority carrier in a p-type material? It's the n. Like I have majority p, minority n. So the current will be due to the minority carrier, which is E dn del n by del x. That's the diffusion coefficient, and that's when we derive the diffusion current. The same thing apply for the current due to the hole, which is due to the minority carrier in the n type. And in this case, we say if we have a uniform doping, then the N0 and P0 are independent of X. There is no change with them. They are in the uniformly doped, so they are the same. And the low level injection condition prevail then. So these are the statement that we will lead us to the derivation of the minority carrier diffusion equation. Now we will go back to the continuity equation and we will write it in this form. I have del of n by del t. I have the change with respect to the neutral plus delta n by delta t, And as we said, we took these assumptions, we said that we have a uniformly doped material, so the N0 does not get effect with the position, so we will be left only, sorry, back. So we will be left with the delta N by the change of delta N. So it's only the change of the excess carrier, and for the current as well. So it becomes del N, dN, del square of delta N by del X square minus delta N by tau N. So now we have reached this equation. The same thing for holes will apply, and we can then take the case for steady state condition, which we will see in a minute, and how we will get the condition. So in here, I'm just giving you the two equation, which is delta of del NP by del T. Now you're going to tell me, why did you include that subscript? This subscript is to tell me that I'm talking about minority carrier in the P region. Here I will be talking about minority carrier in the N material. So that's why as well you have to keep in mind, if I'm talking, let's say, about only P material, I will say the P subscript P times N subscript P equal to Ni squared. So you see the product of the two will keep it as Ni squared. So that's what it will not change. And these we will be going into detail when we will be talking about the PN diode. On Thursday, we will start with the PN diode. And the derivation for as well the current due to recombination generation will be included as soon as we will be talking about the real diode. We will be talking first about ideal diode and will derive the ideal current. Then if we will add the rate of recombination generation, then we will be including the derivation of the current due to the generation recombination. So for now, then we're talking about these two equations that are corresponding to the minority carrier diffusion equation, and then from that we can go to the steady state equation. In steady state equation, what does it mean? If we have no diffusion current, what does it mean if we have no recombination generation as well? So as well, before I will state the steady state, the diffusion current, and the recombination generation, I want to show to give you this equation. That's always we refer to the diffusion length. The diffusion length equal to the square root of the diffusion coefficient multiplied by the time that it took to diffuse across. Okay, steady state, it implies that the total flow rate is 0, okay? And of course here, the total flow rate, we're talking about only the excess carrier, and the same thing for N or for P in the material. If we have no diffusion current, that implies that this term from the previous equation will be 0. If we have no generation recombination, then the loss rate is 0, because you know the loss rate is due to the generation recombination inside the material. So now we will only take the special case of the steady state in order to see what we can obtain from the current. So the general solution then of the equation for steady state become this term equal to that term. where LP, as you know, LP square, it's when we have the dn and the tau n from here. So dn, dp tau p, since it is equal, LP equal to the square root of these two, then LP will be square equal to dn dp tau p. So, and the general will be, if we take we integrate twice, then we will obtain that the change of, or the excess carrier will equal to this equation, a e to the minus x over LP plus b e to the x over LP. Then we will determine the constant where a and b are the constant. So you take the boundary condition, you set when x equal to infinity, this term will add up to 0, and when this term x equal to 0, then we will obtain it's equal to del p of n sub 0. Therefore, we will write the solution, the general solution then of the excess carrier of del p equal to del p e to the minus, of course here of 0, subscript 0, e to the minus x over LP, and this is the presentation of the graph which correspond to the excess carrier Pn as a function of length over the diffusion length. Okay, I will stop here for a minute to ask if anyone have a question before I will introduce you to the last few slides that we have concerning about Poisson equation, which we will need it for the PN diode. Is everything clear?
Yes, doctor.
Yeah, doctor.
No. I guess there isn't many students are present in this lecture. Okay, so before I go into this two equation, I want to tell you that you will be responsible for the derivation of the continuity equation from the first step when we introduce how the current enter into the semiconductor and the current getting out of this semiconductor. So we have to go through all these steps and then to reach to the last statement that we have for a steady state condition. Of course, when we will finish from PN diode, I will be doing as well a exercise session, which will show you or give you an idea how a question can be posted to you in an exam. Sorry, let's go back. Okay, so when we said when delta n equal to delta p, but they are not equal to 0, this implies then that NP does not equal to Ni square. Okay, so in this case, what it means that we don't have a uniformly doped material. So in this case, then we'll say, okay, since NP does not equal to Ni square, how can I then write this equation relating to Ni? But we will say that these relations will always be preserved and we'll use them. So we'll say, okay, in this case then, N still equal to Ni e to the EF minus EI over KBT, and P equal to Ni, which is Pi, is the same thing, e to the EI minus EF over KBT. When I write I, it means Fi, the intrinsic Fermi level. So this equation then, if I'm writing this equation, this implies that I took already NP equal to Ni square. However, this is not really true for the condition if I'm saying that delta n equal to delta p, but we're introducing in that case two new levels. So if I want to go from these two equations to have this condition delta n equal to delta p, then I have introduced the two Fermi level, the Fn and the Fp. Since you know that if I'm talking about an N-type material, the Fermi level, we know that it will be closer to the conduction band. This Fn will be close to the conduction band, and this Fp will be close to the valence band. So I can go into these equations based from or deduce them from these equations where n and p were equal. Okay? And in here, I want to present to you Poisson equation, because with the Poisson equation, we will be needing it for the electric field in the PN diode. As you see here, if I have an electric field passing through the semiconductor material, when it gets out of the material, it will be a different electric field since it passes through a thickness of delta X and a cross-sectional area A. So again, we will be relating, from Gauss's law, you know that the change dE by dx equal to the charge density over the permittivity, and the permittivity here, since we are not in free space inside the material, it will be the permittivity of the semiconductor material we're using. So this equation, you will need it as when we will apply a current, an electric current through the semiconductor, through the PN diode, and we will relate this to the depletion region. If you recall, we will have, when we have a PN diode, we have a depletion region. So we want to understand how the depletion region and the concentration of the electrons and holes affect the current, the passing current through the material. And in here, the charge density, what we are saying that the charge density then equal to the E, because we are talking here about a completely ionized system. So the charge into P minus N plus ND minus NA, that equation came from P plus ND equals